Hello, dear students. We come today and do this topic on radioactivity. It is a subunit on the unit just which follows topic on catalyst. Now, radioactivity is something we talk of in our day-to-day lives. In fact, many of you have heard of so much on this topic, especially in our area here. Whereas certain areas in our vicinity where a lot has been it's been on the news lately about radioactivity and nuclear material, etc., and you must be wondering what is this radioactivity. In fact, it is a very important topic in today's world where we focus so much on the radioactivity that it can be used in many different ways, both for specific purposes as to uh, for safe management and for safe in fact rather I would use the word safe use of radioactivity. But before we go into what radioactivity is, let us go back to the early stage of chemistry when you started learning chemistry, and that is when you started to learn and study about the structure of the atom, which is one of the smallest units in chemistry. As we all know, structure of the atom is composed of a nucleus and a cloud of electrons that revolve around it. And here we can see that the nucleus is made up of the protons and the neutrons, where the protons are positively charged and the neutrons are neutral. And what revolves around it is the electrons. And the electrons revolve not in specific orbits, but in uh, they are very random and they move around the nucleus and they don't fly out until and unless an energy or a force is being applied to it. And this is what we've learned in your early classes about the structure of the atom. And you all know that electron is negatively charged. In fact, for an atom, we know that protons cannot be removed from a nucleus, while electrons can be removed. So if you remove an electron, uh, the atom becomes positively charged. Why? Because the number of protons is always equal to the number of electrons, and when you add electrons, the atom becomes negatively charged. So this is basically what the structure of the atom is. Now, atoms of an element may have different mass number but the same atomic number, and such atoms are known as isotopes. Now we all know that the number of protons is the atomic number of that element. Suppose we take for example carbon. We know that carbon, the atomic number of carbon is 6. And when we say the atomic number of carbon is 6, that means the number of protons is 6. So here we have 3 different carbon atoms. They are all carbon, so that means the atomic number is 6. So if the atomic number is 6, that means all 3 they have number of protons equal to 6. Now these carbon atoms, you can see here the 3 carbon atoms, and they have 3 different numbers there, 12, 13 and 14. And what do these numbers signify? These numbers, they signify that this is the mass number. So if it's a mass number, that means carbon has 6 protons, and in the first case it has 6 neutrons. So if you add those two, you get the mass number is equal to 12. In the second carbon atom, you see the number of protons is also 6, but the mass number is different, which means the number of neutrons is 7, and that adds up to 13. And the third carbon atom also has a mass number of, also has a number of protons as 6, but the number of neutrons as 8. So that adds up to 14. Now these three carbon atoms are very possible. The change in atom is not important here. Why? Because all three are carbon atoms, so that means they have 6 numbers of protons, but they have different mass number, that means different number of neutrons, and these three carbon atoms are known as isotopes. Now these isotopes may be unstable, or some atoms, in fact many atoms, they have unstable nucleus, and these unstable nucleus, now let's take for example, if someone is unstable, or you are unstable, or you are uncomfortable, what do you tend to do? We do not tend to stay in that position which we are uncomfortable, and we try to find a position which is more comfortable. So same case with atoms also. If atoms have unstable nucleus, they tend to find or do something to attain a stable configuration or a stable position. Now, how does it do this? These unstable nucleus, they undergo a process of decay to attain that stability. And this is being done by emitting some kind of rays. Now, what are these rays? Now, Henry Becquerel, he was the one who discovered these rays. He discovered these rays while studying certain minerals which emit light when exposed to sunlight. And these rays he discovered when he used uranium salts, where he was studying uranium salts, and these uranium salts produced spontaneous emissions that darken photographic plates. And these rays were named by Marie Curie as radioactive rays, and she named the process radioactivity. These rays and particles emitted by radioactive source are called radiation, and that is how the term radiation was coined and how radioactivity was discovered. And we can see carbon, 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 carbon 12, carbon 13, carbon 14 are isotopes, right? Now, isotopes of atoms with unstable nuclei are known as radioisotopes. And these are radioisotopes. They emit that radiation which was discovered by Henry Becquerel and Marie Curie. They emit these radiation to attain a more stable atomic configuration. And this process by which these radioisotopes emit radiation to attain a stable configuration is known as radioactive decay. How does this happen? Let's see, this picture will help you. Now, if we look at the first structure, this is a parent isotope and it is unstable. Now, this parent isotope, when it is unstable, it tries to find a stable configuration. So, how does it attain a stable configuration? It becomes agitated. So, when it becomes agitated or becomes aggressive, we can put it that way, they try to attain that stable configuration by emitting some kind of energy or heat, or it can emit some rays or uh, any kind of radiation, but here it's just this pictorial representation just shows that it emits heat and it attains a stable isotope known as the daughter isotope. Now, what is radioactive decay? Now, we all know that radioactive decay was discovered by Henry Becquerel and named by Marie Curie. There are three types of radioactive decay. The first type is known as the alpha decay, or can be written as the symbol alpha decay or alpha particles. The second type is known as a beta decay or the beta particles, and the third type is known as gamma decay or the gamma particles. Now, let's look into detail about the alpha particle. What is the alpha particle? An alpha particle is composed of two protons and two neutrons. The alpha particle is the same as helium atom. Why helium atom? Because it is composed of two protons and two neutrons. So it has a mass number of 4 and an atomic number of 2. So helium atom has the atomic number 2 and a mass number of 4. So if it's composed of two protons, it means it's got two positive charge. And if it has two neutrons, it means it has a mass number of 4, not plus 4, 4. So it has a charge of plus 2 and a mass of 4. And alpha particles are the largest and the slowest. Why? It's as big as a helium atom and it has the least penetrating power. In other words, it can be stopped by paper. It can also be stopped by skin or your hand. So that is how least penetrating alpha particles. So an alpha particle is written as an alpha with a subscript of 2 and a superscript of 4. 2 indicates the atomic number and 4 indicates the mass number. So this is written in case of radioactivity. This is how 2 and 4 are. Atomic number and mass number are written. It is also written as helium 2 4. Why? Because alpha particle, like we mentioned here, is the same as helium atom. Because of its large charge, the alpha particle has a strong ionizing power. So that is the alpha particle. So let's take an example here. Suppose you have a parent atom, an unstable nucleus, X, with an atomic number of Z and a mass number of A. And this undergoes alpha decay. So what happens? Two protons are removed and 4 mass number or 2 neutrons are removed. So you can see here it's written as Ya minus 4. So if A is 10, so Y will have 6. And if Z is, say, let's say, take for example 5, so Y will be 3. So Z minus 2 will be 3. So this is an alpha decay. So why plus helium? Because one helium atom or one alpha particle is emitted, is removed. Next, look at this. Normally, this is just a representation of how an alpha particle is emitted. So you have the parent nucleus, and the parent nucleus emits an alpha particle where you have 2 neutrons and 2 protons, and that is how it was represented. Now let's take for example a radioactive nucleus. See, uranium 92, 238. That means uranium, which has an atomic number of 92, and this isotope of uranium has a mass number of 238. So what happens when it emits an alpha particle? It means two protons are removed and two neutrons are removed. So the mass number reduces by 4 and the atomic number reduces by 2. So if you reduce atomic number by 2, you get an element with the atomic number of 90, which is thorium. And the alpha particle is the radiation, and the thorium form is the daughter nucleus or the new nucleus. And this is how an alpha emission takes place. Beta particle. Beta particle has a charge of -1. So -1 is what? -1 is the same as an electron. And beta decay occurs when a neutron changes into a proton. And mind you, inside the nucleus. Okay, suppose you have a proton of, say, an atom. So let's take hydrogen with one neutron. So this hydrogen has one proton and one neutron. So when it undergoes a beta decay, the neutron in a hydrogen atom is converted into a proton. So you initially had one proton. So when it undergoes a beta decay, you will get the daughter nucleus will have 2 protons and 0 neutrons. And this will form into a helium atom. Okay, in a beta decay, there is a change in the atomic number, but no change in the mass number. Now the beta particle is lighter than the alpha particle and even faster. So we talked about the alpha particle being bigger, and we talk about the alpha particle being slower, and the beta particle is much lighter and much faster than the alpha particle, and it also has a high penetrating power. It means it can be stopped. It can't be stopped by a piece of paper, but it can be stopped by an aluminium foil. So a beta particle can be written as this: -1, that means you minus one proton, and 0 neutrons. That means no change in the mass number, but number of protons reduces, or is the same as an electron. So like I give you an example of hydrogen. If one neutron is converted to a proton, you get a helium nucleus or helium atom. It means you have 2 protons and 1 electron is being emitted. Okay, this is how we write beta emission. So X in an atom with an atomic number of Z, so it undergoes a beta decay. The Z is increased by 1 while the mass number A remains unchanged. So the -1 in beta cancels with the +1 in X prime, and this is beta radiation. Now this is a representation of a beta emission. You have neutrons, which is blue in color, is converted to a proton. At the same time, an electron is emitted. Now let's take this example. Here we have a carbon nucleus with a mass number of 14. So this neutron, the blue color, this carbon 14 nucleus undergoes a beta decay. And this beta decay, one neutron is converted to a proton. So the atomic number of carbon is 6. So when it undergoes a beta decay, it is converted to a nitrogen atom with 14 mass number. and an electron is emitted. There you see carbon 6 is formed and nitrogen 7 is formed from it. The third type, the gamma emission. Here we have the gammas are waves. The gamma rays are waves and not particles. That means they have no charge and they have no mass. So you have 0, 0. Gamma rays have very high penetrating power. And when you say gamma rays, they are so strong they can even penetrate the skin easily. And it can be stopped only by a thick slab of lead or concrete. Gamma rays travel at the speed of light. That means they're very, very, very fast. And gamma rays are electromagnetic in nature. So when atoms decay by emitting alpha or beta particles forming a new atom, the nuclei of the new atom may be unstable. So we were talking about unstable atoms or the unstable nuclei. So when they undergo an alpha or beta emission, they form a daughter nucleus or a daughter nuclei. And this daughter nuclei may be unstable. So for it to be stable, they tend to emit a gamma radiation. And this gamma energy or gamma radiation has very, very, very high energy. And this energy is emitted as the gamma radiation. There. This cobalt-60, the parent nucleus, undergoes a beta emission. And a beta emission, it forms a nickel uh, nickel atom. So nickel atom, cobalt is 27 and nickel is 28. Nickel atom may be unstable, or nuclei may be unstable, and this instability can cause the nickel to emit gamma rays. So this is how gamma radiation is gamma reaction is written. So here we can see that alpha can be stopped by paper or skin, while beta can pass through paper and can pass through skin. But beta can be stopped by an aluminium foil of around 3 to 5 mm, that is quite thin as compared to, but it's thicker than paper. While the gamma rays can pass through skin, it can pass through paper, it can pass through aluminium foil. So what can stop gamma rays? A thick slab of lead. Here in the picture here we can see that the lead is quite thin, but normally you need a very thick slab of lead or thick slab of concrete which can stop gamma rays. So this is what it does to your body. The alpha particles or alpha rays can be stopped by your skin, while the beta can penetrate your skin, but it can be stopped by the underlying tissues. But the gamma rays can go right through your skin, right through your body, and out. So that's how strong, how high the penetrating power of gamma rays are. Here in this table we can see clearly the different types of decay. The alpha decay, the beta decay, and the gamma emission or gamma decay. And here it's very clear. You can have a look at that. This model can help you understand the different types of radioactive rays. Let's take a few examples. Alpha decay. Yeah, uranium 92, the mass number of 233, will undergo an alpha decay to give you thorium with one helium atom. So all the helium indicates its The helium atom indicates it's an alpha decay, while the rest also similar. And you can have a look at all these examples here, and you can even practice them if you in your exercise books or your copies or your plain sheet of paper. And beta decay, here are a few examples. We have beta decay of carbon, which forms nitrogen, phosphorus, which forms sulfur, and so on and so forth. So for that too, you can jot it down in a piece of paper or in your practice. You can practice this as you write, because these are very important, and they normally come in every exam, and you have to know how to identify which kind of emission by looking at the reaction. Normally you don't have to know the symbols. Sometimes maybe atoms are not given, or elements are not given. They're given as X or Y or Z, so whatever the case may be, or A. So these you can write down the daughter nucleus, or you can write down the parent nucleus by putting a prime on top of it, or maybe you have another symbol which does not indicate any element. Half-life. Now what is half-life? This will be very interesting. Half-life is the time taken by an unstable radioactive atom to decay to half its original quantity. Now when you say half, suppose I take 10 grams of an unstable radioactive atom of course, if the half-life of that unstable atom is, let's say, 5 minutes, means after 5 minutes of the 10 grams of the unstable atom, only 5 grams will be left. That means 5 grams has disintegrated or has decayed. And each element decays into a new element. Now, why a new element? It's because this radiation occurs in terms of alpha rays or beta rays coupled with gamma rays. Like we know gamma rays, there's no loss in mass number, or no loss or no change in the number of protons. We know that beta and alpha, there is a change in number of protons and also change in the number of neutrons. Like for example, carbon decays into nitrogen and uranium decays into lead. Now the half-life of one element is different from another, and it's always constant. When you say constant, right from the beginning of the earth, the half-life has never changed for a particular element till date. Now let's look at what half-life is. Now for example, for carbon to be converted into nitrogen, you can have a half-life of, it contains a half-life of 5,730 years. So if you take 10 grams of carbon and you leave it there, carbon 14, that is unstable isotope of carbon. So this unstable isotope of carbon will decay into nitrogen, or rather the half-life of carbon 14. So if we take 10 grams of carbon 14, to decay, for 5 grams of it to decay, it will take 5,730 years. Aluminium is 7,40,000, or in other words 740,000. Iodine is 17 million years. Uranium 704 million years. So you can understand, just a piece of uranium will say, if you take 1 gram or so, for it to reduce to half a gram on its own, it will take 704 million years. It means for 704 million years there will be radiation. Potassium will take around 1.3 billion years. Rubidium will take around 49 billion years. So I believe you can see from that number, rubidium has the largest or the maximum number of half-life. Half-life of a radioactive atom is an exponential curve. Why an exponential curve? Now when I say I take 10 grams of an atom, an unstable atom, and it takes, say, let's say 1 year to decay, or say the half-life of that atom is 1 year. Now after 1 year, you will get back only 5 grams. So the next year, you're left with 5 grams. So the next year, that will decay into, the half-life is 1 year. So after 2 years, after the second year, you will not decay to zero. Careful, you have 5 grams. Only half of it will decay. So it will be 2.5 grams. Again, that 2.5 grams for the third year, it will decay the half-life. So it will decay into half of the original size, that is 2.5 grams. Half of it is 1.25 grams. So it will not come to zero. So the exponential curve is that it will not come to zero. You can see here the curve is not touching the x-axis. It is only half of what you have will decay or disintegrate. So after hundreds and hundreds and hundreds of years also, some half of the element is always left. So you're not left with zero. Now let's have a look at the different radioactive half-life. You can see uranium 4.5 to 10 to the power of 9 years. 10 to the power of 9 is billion. Okay, thorium takes only 24.5 days. Protactinium, it takes only 1.14 minutes. Uranium-234 takes 2.33 into 10 to the power of 5 years. And look at the radiation it gives out. Uranium-238 it emits an alpha radiation, then a beta. Thorium emits a beta radiation, protactinium beta, and so on and so forth. As you can see there, what is the stable atom? Lead is the stable atom. So uranium-238 is very unstable. So like we said, an unstable nucleus will tend to decay. So it will decay, it will emit radiation until it attains a stable configuration. So this stable configuration is nothing but what? Lead. So until unless it attains lead, then the atom will not be stable. Now here are a few problems I want you all to do regarding the half-life. For example, let's take an example and I will teach you how to do it. If you have 100 grams of a radioactive isotope with a half-life of 10 years. Okay. So how much, let's look at the question. How much of the isotope is left after 10 years? So if the half-life is 10 years, it means after 10 years, half of it will decay. So you're left with what? 50 grams. Second question, how much of the isotope is left after 50 years? Now we take 10 years. After 10 years, you have 50 grams. After 20 years, you'll have 25 grams. After 30 years, you will have 12.5 grams. Okay, after 40 years, you will have 6.25 grams. And after 8 years, after 50 years, you will have 3.125 grams left. How long will it take for the isotope to reduce to 1/4 its original size? 1/4 its original size. 1/4 is what? 1/4 of 100 is 25 grams. So we'll take 20 years. Okay, the half-life of radon 222 is 3.8 days. How much of a 100-gram sample is left after 15.2 days? So 3.8 days, one half of it's gone. Another 3.8 days, that is 7.6 days. Another, the half of the remaining half is gone. Another 3.8, that is 7.6 plus 3.8, that is 11.4. Another half of the half is gone. And after 15.2 days, half of it is gone. So let's take this 1000 grams you have. After 3.8 days, you will have 500 left. After another 3.8 days, that is 7.6 days, you will have another 250 grams. And after 11.4 days, you will have 125 grams. And after 15.2 days, you will have 62.5 grams. Nuclear fission. Now this is an interesting part of the radiation. When a nucleus splits into fragments, it's known as nuclear fission. Fission is splits. So the splitting of a nucleus is known as nuclear fission. This occurs when an unstable nucleus is bombarded with a neutron. So you take an unstable nucleus, you agitate it with a neutron. So this unstable nucleus will split into two different fragments of equal mass or maybe of different mass. But normally it's always of equal mass. And in the process, a neutron is released, and in turn, this neutron hits another unstable nucleus, causing further fission reactions. And when this process happens, or when this process is repeated, is known as a chain reaction. Nuclear fission reaction is always accompanied by a release of large amount of heat and energy. Remember the gamma emission, the gamma rays, and this is how an atomic explosion occurs. As you can all remember, the two bombs that we dropped in Nagasaki and Hiroshima that brought to an end the World War. Like we never had a world war after that, and this was based on this basic principle. And what is that principle? A chain reaction. So all you need was an unstable nucleus and a small neutron. And when that neutron hits the unstable nucleus, it breaks into two fragments of equal mass. And these two fragments of equal mass may be unstable. Most probably they are unstable. And when these two fragments are broken, another neutron is released. And this in turn hits another unstable nucleus or the unstable nucleus of equal mass, and it produces a chain reaction. So this is what happens. You take uranium-235, that is isotope, one isotope of uranium. You just add one small neutron to it. And this forms uranium-236, which is unstable. And this will break into barium and krypton. And in turn, it releases a large amount of energy plus 3 neutrons. And these 3 neutrons can and be used to hit another unstable nucleus, another 3 unstable nucleus. And in turn, this process is repeated. And if you look here, the energy created will cause so much explosion So much, sorry, the energy release will cause an explosion. So this is how it happens. And this is how the atomic bomb was created. And we all know that it killed thousands and thousands of people instantly, and people who had many different problems. Why? Because of the radiation. So much was taken, was so much was uh, destroyed in the bodies of the people living there, and it was a sad part in history. And this process, because of this, nothing was ever repeated since then till date. And no one ever dared use uh, a nuclear bomb, or to say an atom bomb. The opposite of nuclear fission is fusion. So when two smaller nucleus combine to form a larger nucleus, that is known as nuclear fusion. So when atomic nuclei fuse together to produce a nucleus with a larger mass, that is known as nuclear fusion. Fusion reactions produce more energy than fission reactions. So fusion produces more energy. That's even more dangerous. But here it can be controlled. So a large amount of energy is required to start a fusion reaction. And when these are controlled in a lab, you can imagine the energy that is being produced that can be tapped, and it's been used for useful purposes like the generation of electricity and many other different purposes. And nuclear energy in today's world is being used for peaceful processes. The energy of the sun and the stars is by fusion reaction. So you can imagine the distance of the sun from the earth, and how when you stand in sunlight, in the hot sun, we sweat, we feel hot. That is the energy that is coming from the sun, and that energy is the energy caused by fusion reaction. Amazing. So here we have deuterium and tritium. Okay, deuterium is an isotope of hydrogen with one neutron and one proton. Tritium is another isotope of hydrogen with one proton and two neutrons. And when these two fuse, they form a helium nucleus of two protons and two neutrons. But that's not the case here. We have one neutron from deuterium and two neutrons from tritium. And when these combine, you get three neutrons, which is unstable. And these three neutrons cause the atom to be unstable, and one neutron is released, the formation of a stable helium nucleus. Okay, so that is deuterium, tritium fuse together to form helium plus an electron, neutron. Sorry. Same case for here, lithium. Lithium, two lithium atoms can fuse to form carbon, but you need a very large energy to do this. And this energy is so large that it's impossible to do that in our everyday life. So the applications of nuclear chemistry. Nuclear chemistry is so vast and so important that it has a wide range of applications. In fact, all these applications can be searched from the internet, and you can get a long list of applications. But I've mentioned just a few here for your understanding. At first is the generation of electricity. Nuclear power plants use the process of nuclear fission to produce heat in nuclear reactors, and these are controlled. So if something goes wrong, boom, you have a nuclear explosion. and a nuclear explosion can cause so much destruction, not in the immediate aftermath of the explosion, but even for a very, very long time, for many generations, because the radiation is always there. The heat is used to generate steam, which is then used to drive turbines, and then this is produced in this is used to produce electricity. And these are nuclear power plants. And you can see many like these in the world. Second application is in medicine. I'll just go through it. You can search the internet for different applications of nuclear chemistry. Now, in medicine, nuclear energy is a branch of medical imaging that uses small amounts of radioactive material to diagnose or treat a variety of diseases. For example, let's say you want in the field of iodine, for example, iodine 131 emits beta particles, which is used to detect tumors in thyroid glands. New thyroid glands, they use iodine is very important for thyroid glands. So if you use a radioactive isotope of iodine, which is 131, or a mass number of 131, these emit beta particles. And these beta particles can be detected by a specially devised, specially made device which can detect these beta particles, and they can find the tumors in the thyroid glands. And even cancer treatment, like you've all heard in cancer treatment, with the people who had cancer, they had to undergo radiation, and this radiation is the radiation which applies the principle of nuclear chemistry. In fact, for gold or iridium is implanted in or near tumors to try to kill the tumor cells. Even in bone scans can detect the spread of cancer. Technetium 99 can be used to detect bone infection. And in fact, the different scans, the different methods, medical procedures that we have to follow for testing, identification, or for analysis, we have the MRI, which is the magnetic radiation imaging. We have CT scan, is also use radioactive isotopes, and echo also use isotopes or radioactive isotopes. Then we have another application in carbon dating, that is in archaeological studies. This is a method of determining the age of dead matter by calculating the content of C14 present in it. How do we do that? Now we know that everything which is living contains carbon. Even us humans, we have carbon in our body. Plants, dead animals, they all have carbon. So when these dead plants and dead animals they die, like I said, carbon 14 has a half-life of 5,730 years. So this carbon 14 is unstable. In the carbon 14 in our body is unstable, and they decay. And when they decay, they take to reduce to half its original size. They take 5,730 years. And based on the quantity of carbon 14 at this particular time, we can calculate the age of dead matter. Okay, and at death, we know that we can have 100% of C14. Then after 5,730 years, 50% of C14 is left, and then after 11,460 years, 25% of C14 is left. After 17,190 years, 12.5% of C14 is left. And these can be used to detect or determine the age of a dead organism or dead matter. And these are all the three isotopes of carbon are absorbed by living organisms. Another application is in nuclear research, and research is still being conducted even till today also on the cure of Alzheimer's disease, cancer, AIDS, etc. Application is in nuclear research. So much research so much research has been conducted even till today for the cure of Alzheimer's disease, cancer, AIDS, etc. And research has also been conducted to test new developments, new drugs that can be used for the cure of different diseases. Then radioisotope, sorry, has also been used in metabolic studies, environmental studies, and even in genetic engineering. Then nuclear chemistry also finds applications in food and agriculture. And in fact, nuclear chemistry has been used to kill bacteria, insects, parasites that causes diseases. It also used to reduce the spoilage of food. It's also used to improve the quality of food to develop more disease-resistant crops. Another application of nuclear chemistry is in consumer products, smoke detectors, sterilizing cosmetics, hair cream, contact lenses, etc. And then the industrial application we have it finds application to test the thickness of steel, like to detect leakages in pipes or faults in any kind of weldings. For example, if you have plumbing where the distribution of water is from 15 to 20 kilometers away, and detecting a leakage in pipes would be impossible. So what they do is they uh, they in, they insert a small radioactive element which is harmless into the water, and using a sensor they will detect any kind of leakage in the pipes, and also to locate the quantity of oil or natural gas which is below the earth's surface. Nuclear chemistry has been used for these applications. So with that we'll stop here. Thank you.